In Chapter 7, we reminded ourselves of the exponent rules, and we learned about polynomials, and we practiced doing our operations with polynomials. We added, subtracted, and multiplied polynomials. In Chapter 8, we're going to be undoing that multiplication now. So Chapter 8 is all about factoring polynomials. Copy down your target for today. We're going to start off just talking about the prime factorization of numbers and also the GCFs of monomials. So write all the factorizations of 18. How can you factor 18? What can you break it down into? Or basically, what multiplies to give you 18, right? So we would have 1 times 18. What else would we have? We would have 2 times 9. What else can we do? 3 times 6. What else can we do? 4, no. 5, no. And that gets us up to 6, which we ran into here. So there's no other factorizations that will only involve 2 factors, but look at what you wrote. Can you break one of those factorizations down even farther? We can break up 2 and 9 to be 2 times 3 times 3. That's another factorization of 18. 3 times 6 would be 3 times 3 times 2. We can write that down, but that's not really a new one. These are the same, they match, so I'm going to cross that one out. All right, so we have 1, 2, 3, 4 factorizations for 18. Which one of your factorizations cannot be factored any farther? Which one cannot be factored any farther? So when you look at this 1 times 18, can 1 or 18 be factored farther? Yes, we can break 18 apart into whole numbers, so that one is not factored all the way. 2 times 9, well, we broke down 9 into 3 times 3, so this one is not factored, is able to be factored farther. 3 times 6 is also able to be factored farther. We did that here, we just didn't want to write it twice. What about 2 times 3 times 3? Can you factor 2 down? Can you factor 3 down farther? Can you break it up into more whole numbers? No. So this is your one that cannot be factored farther, and it has a name. What do we call it? We call this your prime factorization. So write this down, guys. All factors are prime numbers, and I want you to put a special note on there. 1 is not prime. 1 is not prime. Okay? Just clear that up, because sometimes I know we forget, but 1 is not a prime number. 1 starts with numbers higher than 1. 2 is prime. It's divisible by 2, and it's divisible by itself and also 1. Okay? So the prime factorization is whenever you factor something all the way down to the prime numbers. And we can write 2 times 3 times 3, or really we can write 2 times 3 squared. So that's the prime factorization of 18. Make sure you copy that down before moving on. So if we want to write the prime factorization of each number, you can break it apart, and you can either do a factor tree or you can do a ladder. We're going to do both on the first one. Out on B, you can do either method that you choose. Factor tree is where we start with the number and we break it up into any factors that you know. I might say 40, okay, maybe I did 4 times 10. Then break 4 up again. Where did 4 come from? 2 times 2. Once you hit the prime numbers, you don't have to go any farther. So 2 cannot be factored any farther. It is prime, so we can leave that here. 10 can be broken up into 2 times 10, or sorry, 2 times 5. 2 is prime, 5 is prime. That's as far as you can take it. What is the prime factorization of 40? Well, 40 is equivalent to 2 times 2 times 2 times 5, which is 2 cubed times 5. Don't multiply this out, guys, because if you multiply it out, you're going to get back to 40. You can do it as a check, but I want your answer to be the factorization. So your answer should be a product of prime numbers. The ladder, then, is another way that you can do it. You start with your number and kind of put it in a box, and you divide by prime numbers until you get down as far as you can. So you want to divide by 2 or 3. Start with the lowest prime. 40 divided by 2 is 20. Pull it over a little bit. Okay, divide that. 20 divided by 2 is 10. Notice how I'm traping it over. Each time I take a step over to the right. 10 is also divisible by 2. That gives me 5. 5 is prime, so I'm going to leave that on the outside. Here again is your prime factorization. Okay? Either way, guys, I think I see it more typically as a factor tree. Maybe you learn the ladder and you like that better. Try 98, and you can do it either way, but I want to see the work. 98 is even, so you know for sure it can be broken up into 2 and something. 2 times what will give me 98? This one's going to be 49. 2 is prime, so we're done with that trail. 49 can be broken up into 7 times 7. 7 are both prime, so your answer would be 2 times 7 squared. You can also do the latter, but it's going to look very similar. So we take the 2 out, we have 49. Take the 7 out, and we're left with 7. Prime factorization, guys, 2 times 7 squared. You want to write the numbers, when you look at the bases, write these in order. So 2 comes before 7. I would put the 2 before the 7 squared. Well, we're going to use this idea of prime factorizations to find GCFs. The GCF is the greatest common factor. It's the greatest common factor that 2 or more whole numbers have in common. And I actually just meant to write the greatest factor that 2 or more whole numbers have in common. The product of the greatest integer and power that evenly divides into each term. That's really what you're looking at. So the product of the greatest integer and power that evenly divides into each term. You can also write that down as well. So it's the product of the greatest integer and power that evenly divides into each term, however many terms you may be talking about. Okay, so we think about 160. If I want to find the GCF, I want to find the greatest common factor. We'll break it down. Show me your factor trees or your ladders first. 100 can be factored into 10 times 10. 10 can be factored into 2 times 5 and 2 times 5. Those are prime numbers, so that's as far as I can go. 60 can be factored into 6 times 10. 6 breaks down to 2 times 3, and 10 breaks down to 2 times 5. Guys, basically I'm looking for the greatest common factor, you know, the greatest amount of these that will go into both. So what do they both have? They both have a 2 and a 2. They both have another 2, another 2, and they both have a 5. So our GCF is going to be 2 squared times 5. The prime factorization of 100 was 2 squared times 5 squared. And the prime factorization of 60 was 2 squared times 3 times 5. What do they have in common? They both have a 2 squared and they both have a 5. Try the next one. Again, even if you think you can do it in your head, I would like to see your factor trees or your ladders as your work. So break 48 apart, break 144 apart, and break 96 apart. You can do a factor tree or a ladder. I'm doing a factor tree because I've seen in the past that that's more of what you guys know. So 48 can be broken up into 6 times 8. 6 can be broken up into 2 times 3. Both of those are prime. We're done over there. 2 times 4. Are both of these prime? No, we can go farther with that 4, so it's 2 times 2. So the prime factorization of 48 is going to be 2 4 times, and then times a 3. So it's all the ends. So I'm not going to count this 4, but I'm looking at all the ends here. All right, next one. 144 breaks up into 12 times 12. 12 breaks up into 3 times 4, and then 2 times 2. And we can do that over here as well. Look at all the ends then. What is your prime factorization of 144? We have 4 2's and then 3 squared. Last one, guys, 96. 96 can be broken up into, who knows this one? Give you a little time to think here. Start you off. It's 6. 6 times what will give me 96? It's going to be 16. So you got to think of that on your own. Then break these up until we have prime numbers. This prime factorization for 96 will be 2, and we have 5 of them, times 3. Now when you're determining your GCF, you're going to pick what they have in common. What do they all have? And you want to choose the greatest amount possible. So notice they all have 2's. How many do they all have? They all at least have 4. Do they all have a 3? They do. How many 3's do they all have? Well, this one only has 1, this one has 2, and this one only has 1. So it's going to be 3 to the 1, or you don't have to write that power. So the GCF is 2 to the 4th times 3. I would like you to actually calculate what that would be now. So you're not going to leave your GCF answer as the prime factorization. Find what number that is. This would be 48. Okay? Both are acceptable, but it's good to practice it. This GCF, 2 squared is 4. 4 times 5 is 20. Well, we can find GCFs of polynomials as well. Okay? Again, you're looking at basically what makes up each term, what's the greatest amount that they have in common. So when you're looking at this, maybe look at the x's first. Look at the variables first. This is made up of x times x times x. The second term is made up of x times x. So what do they have in common? They have 2 x's in common. So your GCF is going to have an x squared. You also have to think about the coefficients. You could show a factor tree for 15, or you could break it up into the prime factorization just in your head. 15 is 3 times 5. So this is the same as 3 times 5 times x times x times x. 9 is the same as 3 times 3 times x times x. What do they both have in common then? They both have a 3. Your GCF for 15x cubed, 9x squared is going to be 3x squared. Let's look at your next one. Let's break it up here. 8x squared, break up 8, would be 2 times 2 times 2, or 2 cubed, times x squared. And 7 is already prime, and then we would have y cubed, or you can write them out. What do they have in common, guys? Nothing. So there's no GCF. Alright guys, I want you to try these challenge and geometry problems. Pause the video and then you'll play the next one to see the answers.